Look around you. Every broken glass, every aging face, every dying star is telling the same story. Time only moves one way. But here's the mystery. Almost every law of physics works just as well backward as forward. So why can't yesterday become tomorrow? In this video, I'll show you how a simple idea called entropy may hold the secret to time itself, and why understanding it changes the way you see reality forever. Look around you for a moment. Everything you can see is changing. The coffee on your desk grows cold. A leaf falls from a tree and slowly decays. Buildings weather. Mountains erode. People grow older. Memories accumulate. Every experience you've ever had shares one remarkable feature. It moves from what you call the past toward what you call the future. That seems obvious, doesn't it? Of course time moves forward. We experience it every day. We never wake up tomorrow and remember next week. We never see a shattered glass leap from the floor and reassemble itself onto the table. We never watch smoke gather itself from a room and neatly return to a cigarette. But here's the interesting thing. When physicists write down many of the fundamental laws that govern nature, they discover something surprising. Most of these laws don't actually care which direction time is moving. Imagine filming two billiard balls colliding on a pool table. One ball strikes another, energy and momentum are exchanged, and both balls move away. Now suppose I play the film backward. The balls still obey the laws of physics. The mathematics works perfectly well in either direction. This creates a puzzle that is deeper than it first appears. If the basic laws of nature don't strongly prefer forward or backward time, then why does the world around us seem obsessed with moving in one direction? Why does yesterday feel different from tomorrow? Why can you remember the past but not the future? Why does order seem to become disorder far more easily than disorder becomes order? The answer leads us to one of the most misunderstood ideas in all of science. Entropy. Now, entropy has suffered from a public relations problem. People often hear it described as disorder. That's not entirely wrong, but it isn't quite right either. The word disorder creates images of messy bedrooms and cluttered desks. While those examples can help, they don't capture the true power of the idea. To understand entropy, let's begin with something simple. Suppose I have a box divided into two halves by a barrier. On one side I place 1,000 gas molecules, on the other side none. Then I remove the barrier. What happens? The molecules spread throughout the box. Nobody finds this surprising. In fact, if the molecules didn't spread out, we'd be shocked. Yet here's the curious question. Why do they spread out? There is no tiny law forcing each molecule to move toward emptiness. Each molecule simply bounces around according to ordinary physical laws. Yet after enough time, the gas becomes evenly distributed. The secret lies in probability. There are very few ways for all the molecules to remain crowded on one side of the box, but there are enormously many ways for them to be spread throughout the entire volume. Nature isn't being commanded to move toward disorder. Rather, systems naturally drift toward the most probable arrangements. This idea sounds innocent at first, but it changes everything. Think of a deck of cards arranged perfectly from ace through king in every suit. That's a highly ordered arrangement. Now shuffle the deck thoroughly. Have you created a special new order? Not really. You have produced one of an enormous number of random arrangements. There is only a tiny number of ways to arrange the deck in a neat sequence. But there are unimaginably many ways to arrange it randomly. If you shuffle again and again, the deck doesn't become random, because randomness is magical. It becomes random because random-looking arrangements vastly outnumber ordered ones. Entropy is connected to this overwhelming imbalance in possibilities. Higher entropy simply means there are more possible microscopic arrangements corresponding to what you observe. And once you begin thinking this way, you start seeing entropy everywhere. A hot cup of coffee cools down. Why? The energy in the coffee spreads into the surrounding air. Could all that energy spontaneously return and make the coffee hot again? The laws of motion don't strictly forbid it, But the probability is so absurdly tiny that you would never expect to witness it during the lifetime of the universe. The forward direction of time emerges because probable things happen constantly, while fantastically improbable things almost never happen. This is where the mystery becomes truly fascinating. Imagine you walk into a room and discover a broken glass on the floor. Immediately you know what happened. At some earlier moment, the glass was intact. Nobody needs to explain this to you. But why are you so certain? Because among all possible histories, the one involving an intact glass breaking into pieces is enormously more probable than shattered fragments spontaneously assembling themselves into a perfect glass. Your confidence isn't based on a law that says glasses must break. Your confidence is based on entropy. The future is the direction in which entropy tends to increase. The past is the direction in which entropy was lower. That simple statement may be one of the most profound observations ever made about reality. Notice something extraordinary. When you remember yesterday, what are you actually doing? Your brain contains records of lower entropy states that existed before the present moment. Photographs work the same way. Written documents work the same way. Fossils work the same way. The entire concept of memory depends on traces left behind by processes moving from lower entropy to higher entropy. If entropy flowed the opposite way, your experience of reality would be fundamentally different. In fact, the distinction between past and future might disappear altogether. Now we arrive at an even deeper question. If entropy always tends to increase, why wasn't it already maximized long ago? Why does the universe still have stars, galaxies, planets, and people? The answer appears to be that the universe began in an extraordinarily special state, a state of remarkably low entropy. And this is one of the greatest mysteries in modern science. Nobody fully knows why the early universe possessed such extraordinary order. Yet everything we experience today may ultimately trace back to that ancient condition. Every sunrise, every memory, every living organism, every ticking clock, every historical event, all may owe their existence to the fact that the universe started far from equilibrium. You can think of the entire cosmic story as a long journey from a very special beginning toward increasingly probable states. And that journey creates what we perceive as the flow of time. The remarkable thing is that time's arrow may not be a fundamental ingredient of reality at all. It may emerge from statistics, probability, and entropy concepts that seem almost mundane until you realize they govern the fate of stars, galaxies, civilizations, and perhaps the universe itself. And once you begin following that idea, another question naturally appears. If entropy is really just about probability, then why does it feel so absolute? After all, probability usually sounds uncertain. When someone says there's a 60% chance of rain, you know it might rain or it might not. But entropy doesn't seem to behave that way. A broken egg never suddenly jumps off the floor and rebuilds itself. Ice cubes don't spontaneously form in warm water without a refrigerator doing work. The world seems stubbornly committed to moving in one direction. The reason is that the numbers involved are unimaginably large. When we talk about gas molecules in a box, we're not discussing a few dozen particles. We're discussing numbers so enormous that ordinary language struggles to describe them. A single breath contains more molecules than there are grains of sand on all the beaches of Earth. With numbers that large, probability becomes destiny. It's a little like throwing a handful of coins into the air. If you toss 10 coins, getting all heads is unlikely, but not impossible. You might even see it happen after enough attempts. But imagine tossing a trillion coins. The chance that they all land heads becomes so ridiculously small that you would never expect to witness it. Nature operates with numbers vastly larger than that. So when entropy increases, it isn't because some cosmic policeman is enforcing a rule. It's because the universe continually explores possibilities. and overwhelmingly more possibilities correspond to higher entropy than lower entropy. This means that what we call the arrow of time may be a statistical phenomenon. Now that sounds strange. We're accustomed to thinking of time as fundamental. We imagine it as a river, carrying everything forward. We imagine a cosmic clock ticking somewhere in the background of reality. But perhaps the sensation of temporal direction emerges from something much simpler. Consider a movie. A movie is really just a sequence of still images displayed one after another. Each frame by itself contains no motion, yet when the frames are arranged in the correct order, motion appears. In a similar way, perhaps the distinction between past and future arises because states of lower entropy naturally precede states of higher entropy. The direction isn't imposed from outside, it emerges from the arrangement itself. Now here's where things become even more interesting. Suppose you take two identical rooms. One room is perfectly organized. Every book is arranged neatly. Every object is exactly where it belongs. The other room looks as though a tornado passed through it. Which room contains more possible arrangements? At first glance, people often answer incorrectly. They think the organized room must contain more information and therefore more possibilities. But the opposite is true. There are only a small number of ways for everything to be perfectly organized. There are countless ways for everything to be messy. Move one book. Move another. Rotate a chair. Shift a paperclip. Every tiny change still produces a messy room. Disorder occupies vastly more territory in the landscape of possibilities. This is why maintaining order always requires effort. You clean a room. A week later, it needs cleaning again. You build a house. Eventually, repairs become necessary. You organize files. Over time, confusion creeps back in. Life constantly fights entropy. And that observation leads directly to one of the most fascinating aspects of biology. Living organisms appear to create order. Plants build intricate structures. Animals maintain complex bodies. Human beings construct cities, technologies, and civilizations. At first glance, this seems like a violation of entropy. If entropy always increases, how can life produce organization? The answer is that life doesn't defeat entropy. Life exports it. A plant captures energy from sunlight and uses it to create structure. But in doing so, it releases heat into its surroundings. A human being consumes food and converts part of that energy into useful activity. Yet much of the energy eventually leaves as heat. Local order can increase, provided the total entropy of the larger system increases even more. In other words, life doesn't escape the second law of thermodynamics. Life is one of the most beautiful consequences of it. That's a remarkable thought. The very law often associated with decay and disorder may also help explain why complex structures can emerge in the first place. Stars form because gravity creates regions of concentrated matter. Planets form around stars. Chemical reactions generate increasing complexity. Eventually, organisms appear that can ask questions about the universe. The same physical principles governing cooling coffee and melting ice are connected to the existence of conscious observers. Now let's return to memory. Think carefully about what happens when you remember something. Suppose you remember your first day at school. That memory exists because physical changes occurred in your brain. Neurons formed connections. Information was stored. The memory points toward an earlier event. But notice something important. You possess records of the past because those records were created by physical processes. The act of recording information itself increases entropy. Every photograph ever taken, every book ever written, every computer file ever stored, every memory ever formed, all involve physical changes that leave traces behind. The reason we know about yesterday is that yesterday left evidence. The future has not yet left evidence. That asymmetry lies at the heart of our experience of time. People often imagine that the future somehow doesn't exist while the past does. Physics doesn't necessarily say that. What physics reveals is something subtler. The difference between past and future may be deeply connected to the direction in which entropy increases. That's why we remember one and not the other. Now imagine a universe in which entropy decreased instead of increased. At first that might sound exciting. Things would become more organized. Broken objects would repair themselves. Smoke would gather back into chimneys. Heat would flow from cold objects into hot ones. But if you examine the situation carefully, something peculiar happens. Observers inside that universe would likely perceive time flowing in what they call the forward direction anyway. Their memories, records, and experiences would align with their own entropy gradient. From their perspective, everything would feel normal. This suggests something astonishing. The direction of time you experience may be inseparable from the thermodynamic conditions that make experience possible. In other words, the arrow of time isn't merely something you observe. It may be embedded within the very process of observation itself. And now we arrive at one of the deepest puzzles in all of science. Why did the universe begin with such low entropy? Remember, entropy naturally tends to increase because higher entropy states are vastly more probable. So why wasn't the universe born in one of those highly probable states? Why did it begin in such an extraordinarily special condition? Imagine shuffling a deck of cards and somehow producing a perfect sequence on the first try. You'd immediately suspect something unusual had happened. The early universe appears similarly special. Its entropy was incredibly low compared with what was possible. That fact may be more mysterious than almost anything else we know. Many of the greatest questions in cosmology ultimately lead back to it. Why is there an arrow of time? Why does complexity exist? Why are there stars? Why are there galaxies? Why is there a history of events at all? Each question seems connected to the remarkable state in which the cosmos began. And the more closely you examine it, the stranger it becomes. Because if the universe started in maximum entropy, there would be no meaningful evolution. Nothing interesting would happen. No structures would form. No observers would arise. No questions would ever be asked. The story of everything may depend on the fact that the universe started far from equilibrium and has been evolving ever since. That evolution creates gradients. Differences in temperature, differences in density, differences in energy. And wherever gradients exist, interesting things happen. Wind blows because temperatures differ. Rivers flow because elevations differ. Machines operate because energy differences exist. Life itself depends on gradients. The world is alive with activity because equilibrium has not yet been reached. And in a sense, every process around you can be viewed as part of the universe's ongoing journey through possibility space. And perhaps that's the most extraordinary lesson of all. The arrow of time is not written in the equations as an absolute command. It emerges from probability, from entropy, from the simple fact that there are vastly more ways for the universe to be ordinary than extraordinary. Every ticking clock, every fading memory, every aging star, and every moment of your life is part of that grand unfolding. Yet there is something profoundly beautiful hidden within this reality. The same universe that tends toward greater entropy also gave rise to galaxies, oceans, living creatures, and minds capable of wondering why time moves at all. Out of a cosmos governed by chance and probability emerged beings who can look back at the past, imagine the future, and search for meaning in between. So the next time you watch a glass shatter, a candle burn down, or another year pass by, remember that you are witnessing one of the deepest principles in nature at work. Time is not merely passing. The universe is exploring what is possible, moving from the unlikely toward the likely, from the special toward the ordinary. And perhaps the greatest mystery is not that time only moves forward. Perhaps the greatest mystery is that for a brief moment in that one-way journey, the universe became conscious enough to notice. And that makes every second far more remarkable than it first appears.